All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we will begin. First off, good afternoon. I am Jason Thomas, Project Engineer at America Makes, and your host for today's America Makes Workforce Development Training presentation. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get all the questions answered. Today's webinar is a workforce development training presentation entitled Project 3011, Feature Based Qualification Method for Directed Energy Deposition Additive Manufacturing. Without further ado, it is my pleasure to introduce Principal Investigator Neil Johnson. Neil, I will now turn it over to you and your team.
Hi, thank you, Jason, and thank you all for joining us. Again, my name is Neil Johnson, and I'm a Senior Principal Engineer in Manufacturing Technology Development at GE Global Research. And I'm also the team leader for this America Makes program on feature-based qualification for directed energy deposition. Our partners in this program are GE Additive, GE Aviation, Raytheon, EWI, Youngstown, and Youngstown State University. Today's presentation is intended as a workforce development training and will be a team presentation. Okay. With that, I'd like to introduce and acknowledge the core team members that were instrumental in developing this activity. Okay, we have Shomo Nag, who's the metallurgist and chief experimental design. Shrikar Karanati, who was responsible for data analytics and organization. Yiming Zhang, who's actually been our chief Bayesian Hybrid Model development. Satya Raghavan, who was instrumental in part design and simulation. Chunji Chen, who has been designed for additive and manufacturing. In addition to that, we have a process team at EWI and Youngstown University. We have Dora Chang, Alex Kitt, Lee Kerwin, Eric McDonald from Youngstown University, and Corey Bresna. Okay, as I said, this is a team presentation, and Shomo Nag, Shrikar, and Yiming will be co-presenting with me today. In today's presentation, we're going to provide you with an overview of the technical approach we cover in process workflow, the additive build process, provide you an example of the concept part and show you how we identified the features of interest, provide some description on the design of experiments and the building of the features, and how we extracted the test sample coupons from the feature builds for evaluation. We're going to give you an overview on how we organized and conducted preliminary review of the test data, and then we're going to briefly touch on the characterization of the material set as well, of those builds. And lastly, we're going to get to the heart of the program, which is really the predictive model building and the use and demonstration of that model. So here we have a high-level pictorial view of the program, where we first start off with a part design representative of an aviation and aerospace component we would like to build. In this case, it's a concept part of a high-pressure compressor case. You can see that this part has some features that are typical of what you might find in many components that we may have interest in building and have a challenging time building some of those components. Features like varying wall thickness, intersections of those varying walls, overhangs, penetrations, or holes in the walls themselves. As you are aware, additive affords you the opportunity to use different process conditions to build any of these features and the overall component. But what is not clear is what is the impact that those build parameters may have on the material performance and the overall build. To answer that, we could conduct several iterative builds of the component, section it, test it, until we get the process parameters that provide us with the performance properties that we need. But this would also be very time-consuming and costly. The approach that we've taken here is to extract the features of interest, construct the build DOE around each of them, test them, characterize each of the builds, and then use that data to support a formulation of a predictive model. This page provides more detail and further breakdown of the workflow that we followed through the program. Starting with a component CAD model, we performed the thermomechanical analysis using the mission requirements that the part will see in operation. This allows us to identify the critical features and the required performance or metrics for each of those features. From this, we can isolate the features, develop a build DOE, and test coupon sample plan to follow. Then we conduct several of the builds for each of the following the DOE, extract the sample coupons, conduct the mechanical test, and characterize each one of those test samples. We then organize and perform preliminary review of the data for validation, meaningful insights, before using the data to support any of the model building. The DED process the DED process equipment and materials used in this program are a laser blown powder additive system manufactured by RPMI. The specific system that was used was the RPMI 557 machine located at EWI's facility in Buffalo. The material set that we used was the Ti 6 aluminum 4 vanadium powder. This page provides you with a general equipment capability and range of the parameters used in the program. Oh, excuse me. From the equipment capabilities and process control parameters, you can see that there are 7 primary independent process variables: the laser beam or spot size, laser powder, working distance, travel speed, powder feed rate, raw material set, and the nozzle. Okay. These give rise to several dependent variables that are a combination of the dependent variables and are specific to their settings, which result in the actual build results that you would obtain. For example, such as bead width, the bead height, the actual deposition rate or build rate, and the tool path strategy. So there are many process combinations that could be used to build a feature or even part, but what combination will provide the most effective build and give us the required material property performance? From here, I'm going to turn it over to Shomo, who's going to take it.
Thanks, Neil. Good afternoon, everybody. So as Neil mentioned, so I'll help you go through the deeper dive of the process workflow that Neil shared in a couple of slides back. So the images that you have on the top and bottom part of the right side of the chart here shows the concept part, which is the HPC part that we tried off and tested. And we wanted to make sure that we can, first of all, build this part, and then if there are issues with the part, we would try to extract features from those build issues to be able to create the feature-based DOE. So if you look at this part, the color that you see in the bottom right depicts the different build strategies that have been used to build different sections of the part. And what we have done is we have introduced features within this in terms of holes, in terms of wall intersections, in terms of walls with different thicknesses, so that we can actually extract these features out when we need to create the DOE out of. So we were partially successful in building this. So some parts build very well, some parts didn't build as well. But that was the point in terms of optimizing DOE based on the feature of choice. Neil, if you could go to the next chart. So in order to extract these features, first of all, we wanted to see what are the high stress zones or high performance zones, which would be critical for us in terms of the performance of the part itself. The images that you see on this chart are basically created by ANSYS, where we actually created a thermal mechanical model to identify the zones of high interest in terms of criticality of the which could be notches, divots, wall intersections, or thin walls by itself. Neil, next chart. Thank you. So once we had those singled out, you can see there are three different distinct features which we could identify based on the HPC part itself. You have the vertical thin walls, which are of different thicknesses that are built using the DAD process. We have the holes within the thin walls itself, which could be in the rhombus or teardrop shape, depending on what is the choice itself. And then the third feature is where we have the intersections of two different thin walls at a point, and one usually meeting the other at an angle with each other. So these presents us with different thermal scenarios. So if we found that these three sections or these three individual features would be ideal for us to create the DOEs around. If you go to the next chart, this is basically the drop downs. What we felt was important for us to define a feature of interest. So for example, for the thin vertical wall, you can see that it's the simplest out of the three features, where the wall thicknesses and the surface conditions are dependent on the build strategies and the build parameters that are employed. And then we also had some sections of the wall go through the post-processing steps. So the microstructure and the defect structure based on the heat treatments that the part sees was also taken into account. For feature 2 and 3, it's basically a convolution of the thin wall feature with a second feature, i.e. the holes or the intersection three features. So we had to add on stuff like hole sizes, the hole geometries, and also the intersecting wall thickness, which is intersecting at a constant angle of 30 degrees with respect to the vertical wall itself. So in interest of time, Neil, if you could take us, yes. So in the interest of time, we are going to mostly focus on feature 1, which is the thin wall. That is possibly the building block of the BH model and the testing matrix that Shrikar and Yemega are going to talk about next. But the thin walls, again, the types of the thin walls that we use, the thicknesses and the build strategies were all a part of the DOE that we wanted to look into. So let's go into the how we're going to extract the information. So if you go to the next chart. So first of all, we have to build these walls, right? So the way that we looked at it is either the walls are buildable or feasible to build. So the first thing we looked at it was we did some stress analysis to see there are warpage tendencies or crack tendencies or high stress zones that could form at different sections of the wall. So we were really cognizant of these difficulties with builds, depending on the size scale of the wall that we chose. So we down selected those based on this criteria. And once we were able to build the walls, you can see in the bottom left, a bunch of the walls with different thicknesses were built in different build strategies and build parameters being employed. We could actually define a way to extract these samples out. So once we have the walls built, you can actually use the zone-based criteria to look at the top left, top center, top right, or bottom left, bottom center, or bottom right zones. And then also, while we test the samples, the flat tensiles were taken out, taking into account the orientation of the samples with respect to the build direction. So you have the wall build parameters, the wall build strategy, the location from where you are going to extract these samples out, and the orientation of the samples with respect to the build axis, all taken into account when we walk the line from processing, structure to property. If you go to the next chart, This is, just a snapshot of the similar simulation strategies that we employed for the second and the third features as well. So we looked at the walls with holes and walls with intersections, and you can see, depending on what kind of features we're using, you might end up with different regions which are high stress or low stress zones. If you go to the next chart, Neil. So this is basically the layered approach, no pun intended here, in terms of connecting the X's and the Y's as we drive down from processing to structure to the property of the material. So this is just for the thin wall section. So that is where we are going to focus most of our chat today. So if you look at this, the X's are on your left, the Y's are on your right. And what I've done is we have put color codes based on the actual connections with the X's and the Y's. So if you have the build parameters, for example, power, feed, speeds, scan lengths, and beam diameters, all of this is connected to the build characteristics, which is the actual wall thickness that you build and the time and the yield that it took to build those walls, along with the physical properties that were measured in terms of quantities like densities and surface roughnesses. Now, if you take it one level deeper, so if you look at post-processing, which is you extract the samples, you extract the walls from the builds, and you basically subject it to stress relieving or HIP and heat treatment. In that case, we are actually putting a location stamp on it. So once we put the location stamp on it, you have the defects in the microstructure dependent on the location from where you're trying to investigate. So all your lack of fusions, gas porosities, and cracks in terms of defects, as well as the different microstructural features in terms of lathe sizes, grain widths, etc., are all measured in a quantitative fashion, or it can be fed into the BH model here. And then driving out, the last step is the sample orientation and whether we are machining the sample or not. That is intimately tied up with the mechanical properties that we find out in terms of yield strength, tensile strength, elongation, and moduli. So all this information, mind you, are in a quantitative fashion because these are basically the data that could be fed directly into the model. So in total, we had 250 plus tensile testing done for this particular build feature, thin wall build feature itself. 100 plus panels looked at. We made sure that the build scope is wide enough where we could have where we cast a wider net out, and the entire goal was to have a unified model which is data driven from processing to structure and then structure to property assessment. To drive down this further in terms of how we are going to look at this, Shikhar is going to take over from here. Shikhar.
Yep. Thank you, Shamo. Hello, everyone. This is Srikar Karnati. Diving in a little into the parameters and parameter values, one of the primary conditions for creating the training data set in this effort was successful builds, meaning built to completions, be it height-wise or running the full extent of the toolpath planned and successfully building the part. So the parameter combinations that could build a feature or a component successfully were the only ones that were considered for testing and characterization. So this requirement for success leads to correlation among the process parameters. For example, with increasing laser power, the beam diameter and the feed rate may need to be increased. And this can be unavoidable. So for the wall feature, a total of 15 unique combination of process parameter values were chosen. To highlight that, the table here shows some of the principal variables. Now, for the bounds of the for these process variables, we chose a sizable range of the machine and process capability, and parameters were varied at different stages of the planning, building, sampling, and characterization. For example, the independent process variables included, build process. From the build process standpoint, included power, speed, strategy, etc. From post-processing standpoint, it included heat treatment, and when it came to tensile testing, the specifics of specimen extraction, be it surface condition of the gauge length and tensile gauge orientation relative to the horizontal were varied. The table also includes the number of samples we've tested for this particular feature. So in the as-built condition, as-built and stress-relieved condition, we tested around 163 specimens, and in the hipped and aged condition, we tested around 96 specimens. Next slide, please. Right. So now to structure all the data and capture all the context in the specimen sampling and testing, we had to organize the data starting from the left to the right. The left includes the different variables relevant to the building process. At post building, you attain the wall, which is a component, and there you can get surface roughness, physical measurements, and density. From that stage, the component can undergo heat treatment as post-processing. And if you're doing tensile testing, you can sample specimens from different locations and orientations and surface conditions, following which the specimens can be tested to obtain mechanical performance. Yes, taking a step back from a microstructure standpoint, you again take the component, you heat treat it, sample material from different locations within the wall, and that can undergo characterization, and you can once again get measurements of porosity, microstructure measurements such as alpha, lath measurements, etc. So you structure all of this and create a matrix with inputs and outputs clearly distinguished. Next slide, please. So before we hand over this structured data for BHM modeling and training, we want to make sure the data set is valid, and we are supplying data that is representative of the process and doesn't capture any unexplained phenomenon. To accomplish this, we performed a first order analysis, which involved looking for outliers, looking for significant differences in the data, significant variations, if any, with process parameters, possible correlations, trends, etc. So for example, here we have a summary slide, summary plot showing the influence of heat treatment, specimen surface condition, and tensile test orientation for the wall features here. So some of the primary takeaways here is that heat treatment produced a significant difference in the strength performance. We've seen a decrease with the specific heat treatment we've performed on these specimens. Another observation was the surface condition of the specimens may influence the performance of the AM material, both heat treated and otherwise. And the other thing is the gauge orientation or the test orientation of the specimen relative to the horizontal, which so the difference in these measurements is indicative of anisotropy in the material. And with the specific heat treatment that we've chosen here, what we've seen is that the anisotropy may not be completely removed with the specific heat treatment. So with all this analysis and understanding, we are confident that we can hand over this data for BHM modeling, and everything that we see here makes sense and there's nothing unreasonable. Right. Next slide, please. So the process we've detailed so far for the wall feature was also extended for the other features looked at under this program, which includes walls with penetration and walls which have intersections and overhangs. While all the process performed on the wall feature is relevant for the other two, we had to also bring in other process parameters that are contextually relevant for the hole and so the penetration and the intersection overhang features. For example, with the wall with the penetration, you have notches at the corners, you have skin effects such as upskin and downskin, and those features can influence the performance of the material. So we had to factor them into the matrix as well. Right. Next slide, please. Right. So far, we've discussed details on how the input and output variables were structured and handled. However, we theorize there is room for considering and incorporating a lot more aspects into the model. So in this program, we've tracked and documented information at every stage of the process. So this flowchart details the different aspects we've kept track of. So starting with powder characteristics on the top left, to build parameters, physical characteristics of the component that was built, the specimen extraction plan relevant to testing and characterization, and post-processing, if any, and then even the specifics of characterization and details of how what kind of characterization was done and how those specifications were written. So this encompasses all the primary X's which were controlled and uncontrolled, and primary Y's which we're trying to model are the defect microstructure information and performance. So next slide, please. So with all this information, with data cleaned up and packaged, we hand this over to Yiming for BHM modeling, and he's going to talk from here. Thank you.
I will talk about the detailed modeling technologies we have been using, and then talk about the demonstration use of the developed standalone executable. So we have been working on full perspectives for the modeling. The first one is forward prediction with cross validation. So this item is supposed to query the quantities of mechanical property, physical property with given process parameters or microstructures. And then the model is evaluating using cross validation and additional experiments. The second item is the variance-based global sensitivity analysis, so which aims to quantify the influence of each input on the output quantities. The third item is the inverse prediction and optimization. The inverse refers to the process to find the corresponding inputs for desired quantities, either provided by the user or identified from the optimization routine. And the fourth item is intelligent data addition, which refers to the process for iteratively recommend the additive tests with given process parameters for model refinement and validation. And this iterative process is based on BHM prediction to maximize the information gain with limited or scoped experiment budget. The first three, forward prediction, sensitivity, and inverse prediction, will be delivered for the user in the executable. The intelligent data addition is used for us to develop the model and guide the additive builds and testing. Next slide, please, Neil. One key technology of the forward prediction is the GE Bayesian Hybrid Modeling, and we will refer to this as BHM in the following discussion. BHM is rooted in Gaussian process, which is a popular technology to model sparse data set with uncertainty quantification. And the software BHM is originally developed by the National Lab and has been extensively enhanced by GE research team in the past 10 years. We have added additional functions such as sensitivity analysis, robust modeling, and also enhanced the training process with full Bayesian inference. So comparing with open source software, and so we have like tons of features, and together with the robust training process, and also compare with the neural network and traditional linear regression, the BHM had proven to be superior for engineering applications with large data set, and it has been used for hundreds of design problems within GE next generation of designs. For this particular project, we have evaluated BHM against the linear regression, and in general, BHM was around 50% better measured by the R-square on about 10 quantities. So next slide, Neil, please. To initiate the modeling effort, the first step is to develop the initial design of experiment. And we are selecting the additive design in a hybrid manner. So half designs are produced by the additive experts from EWI and GE Research Center to determine the process variables according to the previous successful experience. And then we augment the design of experiments with optimum space coverage, space filling using Latin hypercube, modified Latin hypercube sampling. And it's important for the surrogate model to ensure that we have maximize the spatial coverage in the whole design space. And we visualize the spatial coverage of the DOE using pairwise correlation plot. And so this will be produced for the process parameter, and after that, the post-process will be scoped uniformly for each designed process parameter builds. Next slide, Neil, please. This is the demonstration of the dataset we collected for the thin wall feature. Considering this is a very time-consuming process for additive builds and experimental testing on physical properties and microstructure properties, it's really amazing we can end up with 266 sets of specimen for the thin wall feature alone, and among which we got 15 sets of process parameters and 91 sets of characterization data. Characterization refers to the microstructure measurements. And regarding the process parameter, it refers to the 6 machinery parameters from laser power until powder feed rate, and also include 4 post-process parameters from ground or not ground to specimen location on the wall. And we have collected the mechanical property, physical properties, building information, and the defect microstructure, like around 15 sets of properties. And one interesting observation is the data size varied with the different output due to the experiments and measurements difference, which varies between 140 and 256 data set. So to make most use of the data, we have developed different or individual BHM models for each output separately, and all the developed BHM models are based on the same framework had been discussed before. So the association between the input and output are also identified and provided in this table, and will significantly leverage the experience from our additive expert to initiate this model training. And scientific analysis is used to screen the unnecessary input and for further improvements. So next slide, Neil, please. After developing our first set of forward prediction model, and it's important to validate and estimate the prediction capability. So we are doing the validation in 2 ways. The first way is the popular cost validation process, in which we will divide the data as the training and testing. In this case, we are dividing the data into 10 folds. 1 fold is selected for as testing, and 9 folds was selected for training. Then we iterate this divide and combine technique, and for developing 10 sets of smaller BHM models in sequence, as shown in the plot. And for these 10 sets of BHM, we individually check their prediction accuracy and combine them in the 45-degree plot as shown on the right figure. So in the right figure, the horizontal axis are the measurements of the yield strength. The vertical axis are the prediction from the 10 set of small B-tram models. And the identifiable confidence interval, basically the error bar, is also shown in that figure. So among this 200 data set, you can see the predictions are almost aligned with the measurements, which is implied by the dashed 45-degree line. And that means our prediction matches the measurements pretty well. The R square is as good as 0.88. So R square equal to 1 means that our prediction exactly matches the measurements. And we're using 0.5 as a threshold value to identify acceptable accuracy. So all the quantities lower than 0.5 R square from cross validation will be screened out for this model. And the cross validation error is a smart way to infer the predictive performance at untested points for future use. The final forward model are built based on the training with all the dataset. And at the later phase of this presentation, I will also show validation based on additional experiments in a second phase. So, yeah. So in the previous slide, I presented or discussed the framework for the forward model and prediction, validation. So we have built 3 types of B-tram model according to the described framework. The first site is linking from process parameters to microstructure properties. The second one is from microstructure properties to mechanical properties. The third one is from process parameters to property models. So we have checked the model for each output with cross-validation, global sensitivity, and interaction plots. The demonstration outcome is shown in the bottom 3 figures. So for the tenfold cross-validation, it's discussed in the previous slide. The R square equal to 0.5 is used to screen acceptable models. The middle figure is a demonstration of the variance-based sensitivity analysis. So the horizontal axis are the percentage contribution to the quantities of interest, which is to be yield strength in this figure. And the inputs, including primary inputs, interaction, and also higher order interaction, are all included. The top 15 are produced for the user to visualize. So in this plot, heap and orientation are quantified to be the most influenced one. For heap, the percentage contribution on the yield strength is identified to be around 50%. Using this sensitivity analysis, user could either neglect the quantity with smaller or no influence to accelerate their testing and design process with less reduced amount of experiments. We also examine their interaction plot, according to the sensitivity analysis on the bottom right figure, and to make sure we do capture the overall trend pretty well. A few other sentences on the 3 sets of model. So microstructure to mechanical property models are most general among all the 3 models, and which is independent of the design features and the design conditions. So in next slide, Neil, please. So after developing the forward models for all 3 cases, we would like to extend it with the inverse prediction and optimization. So this is based on an optimization routine and to formulate the bidirectional model. So the inverse part or backward prediction develop the forward models repeatedly to predict the properties from the given process parameter. Optimization routine is introduced for this iterative search, and the input variables and predicted properties would be changed accordingly to accommodate multiple features for different application conditions. And also the input variables will be within the suggested range to avoid potential extrapolation beyond the experiment results. So this is inverse prediction is essentially a robust multi-objective optimization with constraint. And we formulated this inverse prediction in a robust manner. So basically, the B-chain can predict a distribution of the property rather than the mean value itself. So we formulated 3 objectives to guide this optimization. The first one is the maximum likelihood estimation for inverse prediction with given with user inputs. And the second objective is the maximum expected improvements for inverse optimization. And the third objective is the maximum expected hypervolume for multi-objective inverse optimization. All this has been embedded in the executable for the user to be used once it's selected between the different setup. And using this probabilistic setup or robust setup, this inverse prediction can give a unique set of process parameters which are most likely to give the desired quantities. So in next slide, Neil, please. This is a flowchart on the detailed routine or algorithm behind this inverse prediction optimization. The user will first identify the values of given properties. Like yield strength, we are using 134 in this examination. And then the iterative optimization will be initiated upon the genetic algorithm. Genetic algorithm is a popular methodology for semi-global optimization upon the forward prediction. And genetic algorithm will iteratively call the forward model. And the forward model will predict at given input parameters. And then the prediction will be used to calculate the corresponding objective function, either likelihood, expected improvement, or expected hypervolume. The objective will be fed back to the genetic algorithm to evaluate the performance of the proposed process parameter and iteratively search until meeting a stopping criteria. And then the optimized process parameters will be recommended for the user. For example, the prediction will be also provided. The prediction will not match exactly the user strength to account for the model uncertainty and experiment variation. Next slide, Neil, please. Now we have talked about the forward prediction and backward prediction. Once we developed the first set of bidirectional models, we would like to refine the model with additional data set. One popular way to do that is using adaptive sampling. And we have been developed a software called Additive, which is short for Intelligent Design and Analysis of Computer Experiments. So Additive is a software for to select informed design of experiments and to make most use of the computational budget or experimental budget to improve the model. So the basic process is the uninformed DOE will be first selected based on the hybrid DOE we just talked. And then after collecting the data and build the B-chain model, we will call B-chain model the stochastic prediction and calculate a few acquisition functions. And the acquisition function is the rank of the value of the candidates for regarding the model refinement. Now we are using uncertainty reduction as the acquisition function for model refinement. And Additive will calculate the acquisition function based on uncertainty and recommend the most valuable points for the engineers to do additional builds. So this process is a little had overlap with the backward and inverse prediction regarding the algorithm. And but now instead of optimizing upon the forward model, we would like to recommend the prediction and corresponding process parameters for the additive expert to perform to additional builds. And this technology has been proven to be superior to make most refinement of the model by leveraging very limited additional data set. So next slide, Neil, please. One interesting observation during the additive build is like we found, or actually it's not just for this project. It's a well-known challenge. Like not all the build will be successful. That's the buildability constraint we have been facing. So in order to improve the buildability or feasibility of the additive builds, we introduced two sets of classification models to evaluate the process parameters and to improve the buildability. The first buildability constraint is the empirical fitting between the mass feed rate and the volumetric energy density for the existing builds. We have collected about 13 successful builds, and as shown in the red dots in the figure, and the green region is an indication of the domain with a high successful chance. And all the points fall out of this green domain are deemed as with less success, with less chance to be successfully built. And the second classification model is based on the Gaussian process classifier for preferred features. And during the build, we would like the wall or some features. For example, for the thin wall, we would like the wall to be tall enough, like larger than 4 inch. So we are building a classification model to identify the process parameters, which is more likely to given high walls. And in this case, we came up with a binary classifier, give you whether it's preferred or not preferred. And using this buildability constraint and a Gaussian process classification model, we successfully removed about 50% of the design space, which is less likely to be buildable, and then perform the additive build only in the remaining preferred domain. So in next slide, Neil, please. Then we, after screening out the successful and the domain with more likely to be buildable, and we performed edits to identify the few points with estimated uncertainty reduction as shown on the left figure. So the horizontal axis are the number of recommended builds. The vertical axis are the estimated uncertainty. So as you can see, with a few points, like 5 points from recommended from edits, the estimated uncertainty could be reduced by 50%. And that also means our B-chain model could be improved by 50% than current one with 5 additional walls. So using this estimated uncertainty, we recommended 5 walls to be built for model refinement, and we also examined the buildability constraint is strictly satisfied, and we also visualized the pairwise plot. And next slide, Neil, please. For the additional builds, this is a quick demonstration of the additional builds. And we have finally selected 5 edits builds and 2 expert builds. And we also recommended 4 walls. 2 walls are aiming for forward prediction and validation. And 2 walls are aiming for backward validation. And all these walls have been carefully examined from the pairwise plot to ensure spatial coverage and also pass the buildability constraints. And in the later results demonstration, I will show the model refinement validation and also the difference of the uncertainty. So next slide, Neil, please. So in this slide, it takes like a few months to finish the additional build for model refinement and validation. And so according to the edit recommendation, thankfully we can recommend a bunch of builds rather than 1 point at a time. So the left figure showed the model validation on the additional build. The blue dots are the previous data set for the training of the initial B-chain model. The black dots are the prediction on the validation dataset. So the horizontal axis are the measurements. So you can see the error bar is also provided from the BHM prediction and based on 95 confidence interval. So you can see the prediction is almost aligned with the measurement for most cases, and even for a few cases, the error could be large. For example, the leftmost point, the black dots, the prediction is around 140 ksi. The measurements is actually about 125 ksi. And even for this case, we got about a 10% error. Our BHM model can still identify the larger error with a larger error bar, and the error bar can still cover the prediction error. So to handle the prediction uncertainty, and we would like to be our predictions to be conservative rather than optimistic, to stay safe for additive design and aerospace design cases. So for this case, we introduced the concept of conservative estimate, which is based on the lower 10th percentile of the BHM prediction. So the BHM prediction assumed Gaussian distribution for all the cases. And for Gaussian distribution, we calibrated the mean value based on standard deviation to allocate the lower 10th percentile. The lower 10th percentile is used as an estimate of the conservative predicts. So on the right-hand figure, it's a demonstration of the conservative predicts in the solid blue dots. So you can see the mean value has been significantly lowered using this conservative estimate. Now all the predictions are close to the measurements, and for most cases, like more than 70% cases, it's lower than the measurements. That will be lower our risk for being optimistic and overpromise of the design properties. So next slide, Neil, please. After validating the model to being reliable on the additional experiments, now we update our model with all the additional testing results, and then we estimated the uncertainty difference. So the uncertainty difference is plotted based on randomly produced 100,000 dataset in the whole design space. Basically, we produced 100,000 sets of process parameters like laser power, etc., and then call BHM to predict at all the grids and plot their histogram in the shown figure to see the uncertainty difference. The blue histogram is an indication of the old model, and the red histogram is an indication of the updated uncertainty. So you can see with additional testing results, the BHM uncertainty systematically increased. And this is due to the introduced uncertainty from testing law, like a testing site, material lot, and motion setup. By performing these experiments and additive build at a different location and with additional uncertainties, the dataset itself has become larger with larger uncertainty, and our model can capture this increased uncertainty with larger prediction, like an error bar. Now the updated model is more reliable with increased uncertainty to reflect that. So next slide, Neil, please. So after performing the addition test and update our model, we have developed a standalone executable to be delivered for the American Makes user. And this standalone executable will support bidirectional modeling and with sensitivity plot. The key files are the folder named models and the executable called FBQGUI. So the models stored all the local files from our developed algorithm. And for the executable, it will support different model direction from forward, backward prediction, backward optimization, and different model type, either from process to property, process to microstructure, and microstructure to mechanical properties. And we are also supporting full features like a thin wall, wall with notch, wall with deviate, wall with intersection. And the sensitivity will be make optional if the user want to check it and further like a screen of the input parameters. The right figure is shown of the forward prediction GUI model. The user will predict, will input the corresponding beam diameter, etc., until ground and no ground, and predictions will be calculated in about 1 second at the lower bottom for all the quantities available. So next slide, Neil, please. Now I will talk about briefly 3 examples on the case. So the first example is the forward prediction, and the steps has been labeled also in the tutorial. The user can follow the step 1 until step 10 to achieve the purpose. And for the forward prediction, the model direction will be selected correspondingly, and we are demonstrating this using a thin wall feature. And the sensitivity plot will be output for all the available cases. So in this case, you will see about 9 sensitivity plots for each quantities of interest. And in the right-hand figure, we are showing the prediction with from 1 validation dataset. Now you can see the after input all the corresponding properties, and we got experimental measurement to be 134 KSI, and our prediction is 138 KSI. The error is about like 3%. And again, we would like our model to be conservative rather than optimistic. So we can switch to the conservative estimator like type, and input the mean and standard deviation prediction, and also the percentile to be 10. We can get the conservative estimate by assuming normal distribution to get a value like 132 KSI. So the conservative prediction will to be 132 KSI for the user to for the user's reference. So next slide, Neil, please. The second example I want to talk about is backward prediction, and the only difference with forward is like now the user will switch to the backward prediction in the model direction. Then the backward prediction GUI will be different with a new section called objectives to predict. In this case, the user will identify the quantities to predict. Like in this demo, we are showing you the build thickness checked and the yield strength checked. The values of interest are 0.2 inch and 135 KSI. So after the identified range, which is set to be default to be the maximum range available from our experiments, the user can predict can click the submit to get the predictions, which is about 0.34, and also the yield strength is 137 KSI in this case. The recommended process parameters will be shown in the bottom figure. So in next slide, Neil, please. For the backward optimization, it's pretty similar to the backward prediction. The main difference is in the objects to predict. Now you don't have to provide the specific value to predict, and instead you can just simply identify whether it's minimized or maximized with 0 and 1 to indicate. We have put a note here. The optimizer routine will automatically produce the maximum yield strength to be 152 for this selection, and the recommended parameters are shown in the bottom. Here, now I have here are all the materials from the Bayesian modeling, and I will start to switch to the live demo of the executable. Neil, if you don't mind, I will share screen from my side.
Jason, will you give Yiming.
Just want to make sure. Neil, can you see my screen?
Yes.
Okay. So this is the demo of the file you will obtain from our team. So you will see the folder called the models, and if you click, you will see all the categorized local files. So, and in the we'll also provide a slide called FBQ executable examples, and you can refer to it for quick trial. And we also have a note to give you all the potential tips for using. And for using the executable, you double click on the FBQ GUI. It will take a few seconds to open the executable. Now this is the main window or starting window you will see from this executable. And first, let's repeat the example 1 from our slide. And in this slide, I would like to show you the detailed numbers we use for the validation data. So you will first select the forward, and then let's select a process to property and a thin wall. Let's also check the sensitivity plot. Then hit complete. And now sensitivity plot is generating on the screen. Let me show you one case. This is the sensitivity plot for the yield strength, and you can refer to the name to identify the corresponding properties, and all the sensitivity plot will be produced. Now I'm showing you the volume, and you can see the sensitivity. And the horizontal axis are showing you percentage contribution to identify the most important ones. And here are the forward model GUI. And in the slide for the first sites, for the first validation, we have beam diameter to be 0.1 and mass feed rate to be 8.3. Average second length to be, the word a little bit small. Let's make it larger. To be 30, 0.02, 38. For scan velocity equal for 0. And 150 KSI for laser power. Orientation means how do you cut the model? How do you cut the specimen actually? For ground, 0 means no, and 1 means yes. Now, after hitting submit, we get all the predictions in about 1 second. So there are 2 columns for the prediction. The first one is the mean value, and the second one is the corresponding standard deviation while assuming normal distribution. And for the validation, we were measuring the yield strength. Now you can see we got the same numbers, like about 138 with the standard deviation to be 4.26 as they show in the slide. The experimental value is 134 KSI. Now we got our prediction is almost at within 3% or 2% error for the first validation point. So after getting the mean and standard deviation, in order to perform conservative estimates, you can hit the conservative estimates button and then type in the corresponding mean value 138.06 and the standard deviation, which is 4.26, and percentile is default to be 10. It could be also adjusted according to different level of confidence user preferred. And after hitting this collection, it will give you 132. And in next slide, we will show. Then I will show a second example for the backward prediction. And for the backward prediction, the only difference we will select the backward prediction. And let's turn off sensitivity plot to simplify this observation. And then the user will get the objectives to be identified. And for demonstration, let's select the yield strength, which is the most popular one to be used for engineering design. What number should we have? One number we can have is like a 100, maybe 140 KSI. And also, the range of parameters could be adjusted accordingly. But we would recommend the range should be within the default ones to avoid extrapolation error. And it could be adjusted to accommodate different machine setup and material availability. So after identifying all this setup in objectives and range of parameters, the optimization routine could take about 2 minutes for to be completed, because this is an iterative search upon the genetic algorithm. So the forward prediction is actually being called again and again. That's why it takes a little bit of time rather than real-time prediction. Another heads up is for the backward process, the optimization routine will take a little bit more time if you have multiple objectives, especially for multi-objective optimization. But in general, it will take about like 1 or 2 minutes to complete one set of example to explore with. And while we are waiting, one shortcomings of this is like we don't have a loading bar to indicate how much calculation is remaining. And that's why we have a note to provide all the tips. Like it usually take like a few, like 1 or 2 minutes to wait. And so please don't stop it while it's still running. Otherwise, the software could be closed. Now the yield strength, the backward prediction is done, and the yield strength predicted to be 140.01 with the KSI to be 1.2. The bottom sections will show you the recommended parameters. For example, like build diameter is like 0.05, and the feed rate is optimized to be 5.72. And if you compare with the range of parameters, they are strictly within the identified range of variables. Now we will show the backward optimization. So for backward optimization, the GUI will be pretty similar to the backward prediction. And the only difference is like we just showed is in the objectives to predict. Now we first select the yield strength to be the properties to be optimized, and put 1 to indicate whether it's a maximization problem. And for the backward optimization routine, it's because we have like a robust objectives, and which makes it a little bit slower for calculation. For single objective, it could take like 2 minutes, 1 to 2 minutes to be completed. If you have multiple objectives, like 3 objectives selected from the first section, the process could take about 10 minutes. So this is something to keep in mind, and for the testing. And we have put tips in these notes to be used. While we are waiting, maybe I can show attach the example slide. And in the example slide, we labeled all the buttons to be used, just in case the user wants to revisit for their own trial and play, and with some explanations on all the buttons and all the flows could be produced. And also in the notes, we provided like we are still adding a few like notes. For example, the models and executable should be put in the same directory to run, and also the size of the GUI window are fixed. It's not unfortunately it's not scalable for this version, and the executable would close if you forget to set up, for example, check, and also give the detailed numbers. Now, the backward prediction and optimization is shown to be done. Like you can see here, the optimum yield strength is identified to be 152 KSI, with the larger uncertainty to be 20. And larger uncertainty is expected because we are trying to find the extreme value, which is usually far from our design point. And the recommended parameters are shown in the bottom figures. So from here, I will complete my discussion on the modeling, and I will switch to Neil Johnson.
So thank you, Yiming. So this really concludes our presentation, and we can open up to any questions that anybody might have. Jason?
All right, thank you very much. We'll now head into the Q&A session. If you have questions for our presenters and you haven't done so already, please type it into the chat box. I do have a few questions here. So the first question I'd like to ask is, how can our attendees or anybody who's interested get a copy of the BHM executable?
So this is going to be available to all the American Makes members through the American Makes data front or storefront. Jason, I don't have the specifics on how that will be there, but you'll be able to download it from your American Makes site once it's transferred over.
Okay, great, thank you. All right, another question here. What acceptance criteria were defined in order to determine mechanical testing validity, and how did the team arrive on this criterion?
Shomo, you want to address that?
Yes, Neil. So the mechanical testing criteria was based on the fact that we were targeting at least a range around the as-cast values. So that was our target numbers. And we were basically extracting the samples from the walls that were buildable. So if let's take from top-down approach. So we kind of define a build space, a build parameter, and we go ahead and build it. If we are successful in building a particular shape of the wall, a size and shape of the wall, which was basically, we kept the height and the length of the wall to be constant, 6-inch tall and 10-inch wide. And the width of the wall was dependent on the build parameter of choice. Once we were successful building to a certain height of the wall, we thought it's a success. And then we could extract the samples based on the location specific to the wall itself. In terms of the data, anything that was so especially for the features with divots and notches in them, we found that the data in some of the cases were much lower than 80% of the average strength that we would expect. We would not consider that, so we would consider that as a failed test, and we would only consider locations where the tests were within the 80% of the average as-cast values. But having said that, for most of the conditions, we were actually above as-cast numbers, certainly for as-built conditions, but also for post-HIP conditions where we basically see a quiescent feature of interest. Does that answer your question?
All right, thank you. So let's see, we got a couple more here. What was the post-HIP aging completed in air, under hard vacuum, or an argon atmosphere?
Again, Shomo.
Yeah, so all of this was done in an argon atmosphere because we were doing it in post-aging. We were quenching at a faster rate, like air cooling, so we couldn't do it in a vacuum atmosphere. But we made sure that they were done all in argon atmosphere.
All right, So let's see, you mentioned as-built and machine surface finishes were evaluated. What was the machine surface finish target? Is this an RA or SA? Did you measure characteristic surface roughness for as-built surfaces, and what were those typical values?
Oh, got it. Don't know the answers to these directly. Shomo, do you happen to know the answers to those? I don't.
Yes, so for the as-built surfaces, we did measure the RA values. And for the machine surfaces, we had a particular grind value, which I don't recall right now, but I can get back to the person who asked the question, because I have those actual numbers which we looked at. But that's a great point, because we actually saw a big difference in terms of surface roughness, which was a big player in terms of the strength debits.
Okay, great. And we're going to provide an email here at the end so that anyone who has follow-up questions can reach out and get those answers. So let's see, we have a couple more here. Is the stopping criteria for your GA a predefined number of iterations or a residual? Is this a tunable user-defined parameter with the backwards optimization executable?
For the GA, we do have a predefined like a maximum number of iterations, and also a stopping criteria included a consecutive like variation of the objectives. So it's embedded in the executable already.
All right, thank you. Let's see, will a copy of the IDACE algorithm be available to members?
The IDACE software is a part of our design process, and it's not ready to be delivered for this executable yet.
Okay. Let's see. Given your observations of the predicted 10th percentile tensile behavior, do you feel that there is sufficient evidence to pursue further development of DED technology for critical applications, which may require conservative estimation using -3 sigma?
Neil, would you like to answer this question?
I would defer. I don't think that, well, I believe that there's further exploration for DED and an opportunity for pursuing DED and use in the aerospace and aviation business, but I'm not qualified to answer what level of sigma and what use in terms of qualifications required for those businesses.
All right, so let's see. How does a BHM differ from a neural network model?
So they're serving the same purpose of predicting quantities from given inputs, but the mathematical foundations are quite different. Like they are different modeling technologies, and BHM is a non-parametric technology which has much fewer parameters to be trained, and so that's why it's superior to handle sparse data set with a larger noise. At the same time, the architecture of BHM is robust, because it's non-parametric. Non-parametric means you don't have to play with all the architectures and the parameter setting. So this has been a known problem for neural network, and also that aside from the different mathematical framework, and empirically, the Gaussian process-based technology has been well known to be superior with sparse data set, and BHM, which is BHM foundation, and a neural network has known to be superior with highly nonlinear response with massive data set. So for DD process and engineering data set, in which we usually suffers from like data sparsity and noise, that for that case, BHM is superior, has shown to be superior. And another thing, like we have extended BHM with some functions like sensitivity calculation, and all these are not available for standard neural network. And the stochastic prediction of BHM is the foundation for edits and the conservative estimates, which is another features.
Okay, thank you. Let's see, given your experience, what more would be required in order to substantiate a B basis allowable for this DED process?
For B basis allow, yeah. Neil, go ahead, Neil.
Go ahead.
Yeah. So, like Neil mentioned, we are not ready to answer how do you qualify the DED process parameters like B basis allowable, etc. And we borrow the concept of allowable, and to give a reference number, we call it a conservative estimate. But they are different in two ways. The first one, B basis allowable quantifies the confidence interval of the lower 10th percentile. But here, we just predict the 10th percentile from our BHM model prediction. So that's the mathematical difference. And but we believe we should do more investigation on the qualification and conservative estimates of DED process.
All right, thank you. So going into our last question here. Is the uncertainty values output from the model equivalent to a standard deviation? Otherwise, how is that defined?
Yes, for the uncertainty quantification, I was mostly referring to the standard deviation information, like shown in the histogram. That's the standard deviation from the BHM models. And all the other derivations is based on the normal distribution for the conservative estimates and the edits and also the robust objective.
All right, great, thank you. That's going to wrap up our Q&A, and that will wrap up today's America Makes Workforce Development Training presentation on Project 3011, Feature Based Qualification Method for Directed Energy Deposition Additive Manufacturing. I would like to thank Neil and his team once again. If you have further questions for our presenters, please reach out to them directly at johnsonna@ge.com. That is johnsonna@ge.com. A copy of this webinar will be available on the America Makes digital storefront for members, as well as the America Makes YouTube channel for anyone who would like to view it. There will be a post-webinar survey going out to all those who participated. We do really appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. Thanks again, and have a great day.
Thank you, Jason.